Okay, well, we've accomplished a lot here. We've shown that disturbances in the electromagnetic fields will propagate through space as waves at the speed of light. Okay, pretty good. We've also shown that electromagnetic waves have to be transverse waves, not longitudinal waves, at least when they're moving in a vacuum. And furthermore, we've shown that the electric and magnetic components of the field are perpendicular. All right? And that in conventional units, the electric field is stronger than the magnetic field by a factor of C. So, well, very good. In this last video, I'd like to kind of wrap that up, but I'd also like to talk about a phenomena that is associated with the transverse nature of the electromagnetic field, and that's the phenomena of polarization. All right? We'll just touch on it, but this is a nice point to introduce that. Here, hang on. Okay, so in summary, Maxwell's equations support electromagnetic waves. The propagation speed of the waves is, of course, the speed of light. Well, the waves are transverse. And we found that the electric field is perpendicular to the magnetic field in these waves, and that the magnitude of the electric field is equal to the magnitude of the magnetic field times the speed of light. Okay? Perfect. And based on this, we can make kind of a sketch. Here's a sketch of a harmonic wave moving through space. The blue here shows the oscillations of the electric field. If this is the electric field, then the magnetic field of our wave would be also a harmonic wave, and it will be perpendicular. Like so. And our wave will move in this direction. Okay? That's our picture. But there's something else that we've shown. Because the wave is transverse, we can actually have two independent polarizations. So, for example, for a wave that is moving in the z direction, we can have an electric field that's pointing in the x direction, or we could have an electric field pointing in the y direction. Or we could have some combination. Like this. Okay. Well, I've just shown the amplitude here. I guess each of these have to depend on uh, position and time in the same way. Here, I'll just make it a harmonic wave. Okay. So, and this directionality, this conforms to our notion of polarization for electromagnetic waves. Here, the formula are a little dry. I'm going to show you a demo, a computer simulation. You might have seen this before because it's one that I like showing in my classes. But here, have a look at it again. Here we go. Let me run my simulation. Can you see it here? So here we have a simulation that shows the electric field as a function of time for electromagnetic wave that's polarized in the x direction. Pretty exciting, right? Here, now let's make it polarized in the y direction. Very exciting. The idea is that the wave is moving out of the page in the z direction. And those are the two polarizations. And of course, we could have some combination like this. Okay. Now we have both an x and y component, and the wave is a combination of this, so the electric field points along the diagonal. We could have any combination. Here's one. And so the electric field vector could point in any direction in the xy plane, any direction as long as it's perpendicular to the direction of propagation. Actually, this doesn't exhaust the possibilities. Here, we're imagining that each component of our harmonic wave is a harmonic wave itself that's oscillating at the same frequencies and they're in phase. But what if they're not in perfect phase with each other? For example, what if the x component and the y component have equal amplitudes, but they're 90 degrees out of phase, like this? Then we get something very interesting. We get a wave, but its polarization, the direction of the electric field, actually changes with time in this simple way. A wave like this is called circularly polarized. This is a left circularly polarized wave because the electric field precesses in the counterclockwise direction for a left circularly polarized wave. If we change the phase difference to minus 90 degrees, we get a similar wave, but now precessing in the right direction. This is a right circularly polarized wave. Well, exciting. I really like this demonstration for showing the circularly polarized waves because it's kind of hard to picture otherwise. Finally, we can have more complicated or less simple types of combinations like this one. Here, the two waves are out of phase with each other, but they're not of equal amplitude. Or this one here. Now the phase difference between the two waves is not 90 degrees, but it's something else. And you can see that in all of these types of cases, even if the amplitudes are equal, the wave amplitude seems to trace out an ellipse over time. And so all of these types of combination are called elliptically polarized light. Anyway, as long as we're talking about polarization, I wanted to show you this. Because light is a transverse wave, we can have two independent polarizations, the two directions that are perpendicular to the direction of propagation. That gives us linearly polarized light, like so. And the polarization vector can point in any direction in the xy plane. Okay? But if we imagine that the two polarization components are out of phase with each other, then we can have combinations like circularly polarized light or elliptically polarized light. Okay? We're just talking qualitatively here, but actually I think this gives a very nice picture that I hope you'll kind of internalize. Okay, well, let's stop our discussion here, and I'll see you in class.